Hello, calculus students. In this video, we're going to learn an integration technique called substitution that allows us to integrate problems like this, where the integrand is a little bit more complicated than we've seen before. So I want you to work through these examples with me, and then when I see you in class next time, you'll have a chance to get lots of practice and to ask lots of questions. So let's go ahead and get started with example number 1. And what we're going to do when we do integration using substitution, if you can remember when you learned the chain rule for derivatives, it's kind of comparable to that. In that you're looking for a function that's sort of the inside function. So that's probably the best advice I can give you right now is you're going to start by, and sometimes it's an educated guess, but guessing what you think what might be the most inside function. So for this first one, our inside function is going to be x squared plus 1. So it's called substitution because what we're going to do is we're going to let u represent that function we chose as our inside function. So u is going to be equal to x squared plus 1. Now the next thing you're going to do is you're going to take the derivative of u. So we're going to find du dx, the derivative of u with respect to x, and that would be 2x. And then what we're going to do is rewrite that. We're going to solve this little equation. We're going to solve it for du. So what that would mean is we would need to multiply both sides by dx. So that would give us du equals 2x dx. All right, so now what we're going to do is we're going to take this integral and we're going to rewrite it, except we're going to make some substitutions. Where we see u squared plus 1, we're going to replace that with u. And then we can take all of this part, the 2x dx, all of that can be replaced with du. All right, so we're going to replace x squared plus 1 with u, and then we're going to replace 2x dx with du. So the new integral would look like this. It would be the integral of u to the second du. Now this is a very simple integral to evaluate or to find the antiderivative of using the power rule. That would be equal to u to the third over 3 plus c. And then the last thing we need to do is just back substitute. Remember, u was equal to x squared plus 1. So let's go ahead and replace that u with x squared plus 1. And our final answer would be x squared plus 1, all of that cubed, all over 3 plus c. And that's our first example. For example number 2, as we look at this integrand, we have 5e to the 5x. Let's choose 5x to be our u substitution. So we're going to let u equal 5x, and then let's find du. Du would be 5x dx. Now let me just explain how I got that. Remember, when we took the derivative of u with respect to x, du dx is equal to 5x, and then solving this little equation for du, we just multiply both sides by dx. So from now on, I'm not gonna write this whole step out. We'll just go ahead and write the derivative of u with respect to x, but we'll go ahead and solve it for du. All right, so then back to our integral. If u is 5x, then that means we can replace 5x. We're going to put a u right there. And then since du is equal to 5x dx, well, here's the 5 and here's the dx. So all of that can be replaced with du. So our new integral would look like this. The integral of e to the u du. All right, we've replaced, just let me point out again, we've replaced 5x is u, and then 5dx was all replaced with du. All right, so then if you recall, the integral of e to the u is just e to the u, and this is an indefinite integral, so that would be e to the u plus c. And then last but not least, let's go back and replace. Remember, u is equal to 5x, so let's back substitute, and we'd have e to the 5x plus c. So in number 3, let's choose this x squared plus 1 to be our u in this problem. So we'll say u is equal to x squared plus 1. Then du would be 2x dx. All right, so now when we go to make our substitutions, obviously we can take the x squared plus 1. We're going to replace that with u. But then if we look at what's left, we have x dx that we want to replace with du, except that du is equal to 2x dx. So what we're going to do is we can't do a direct, straight up substitution because du is equal to 2x dx. So what we can do to balance that out is we're just going to rewrite the integral. We're going to put a 1/2 out in front of that integral, okay, to account for the fact that we have a du that's 2 times too big. So we'd have 1/2 the integral of, we're going to replace x squared plus 1 with u, so that would be u to the second, and then x dx is being replaced with du once we remember to multiply the whole integral by 1/2 to account for this extra factor of 2. All right, so then finding the antiderivative, we'd have 1/2 u to the third all over 3 plus c. And then we're going to do two things. Let's go ahead and replace u with x squared plus 1. And then I'm going to simplify this a little bit. So we would have x squared plus 1, all of that cubed, all over 6. What I did is I multiplied these denominators together. 2 times 3 is 6. And then don't forget your plus c. In example 4, this time let's let u be our radicand, 2x minus 1, and see what happens. So let's let u, oops, I'm about to be black. Let's let u be equal to 2x minus 1. Then du would be 2 dx. du dx is 2, but we're solving that for du, so du is 2 dx. All right, so now we're going to replace 2x minus 1 with u. And then we want to replace dx. Well, we can't straight up replace it with 2 dx, but we can do that if we balance it out by going ahead and multiplying our integral by 1/2. So let's put a factor of 1/2 out in front to make up for the fact that du is actually 2 times dx. So then we could rewrite this then as u to the 1/2 du. Remember, the square root of something is the same thing as raising that to the 1/2 power. It's easier to write if you have a radical, it's easier to write your integrand with irrational exponents because it's easier to find the antiderivative. So we're ready to do that now. So this would be 1/2 times, let's see, that would be, I'm going to go ahead and write the whole thing out, u to the 1/2 plus 1 over 1/2 plus 1, which would be 1/2 times u to the 3/2 divided by 3/2, and remember dividing by 3/2 is the same as multiplying by 2/3, so that would be 2/3 u to the 3/2, and then don't forget your plus c. I should have written it up here as well, plus c. And then simplifying a little bit, we'd have, let's see, these 2's cancel, so 1/3. And I'm going to back substitute. I'm going to replace this u. I'm going to put 2x minus 1 back in. So we would have 2x minus 1 to the 3/2 power plus c. Okay, things are going to get interesting here in example 5. By now you might suspect that we want to let u be 2x minus 1. So let's start with that and see what happens. So we're going to let u equals 2x minus 1. So that means du would be 2 dx. All right, so then as we start making substitutions, this 2x minus 1 we can replace with u, and then dx we can replace with 2 dx as long as we balance it out by putting a factor of 1/2 in front of the integral. So that leaves, so this is going to be 2 du with the 1/2 in front. So that leaves this x. What in the world are we going to do with this x? Well, as you recall, u is equal to 2x minus 1. So here's an equation that I can solve for x, and then I will have something to substitute in for x. So let's take this equation and let's solve it for x. So I'm going to turn it around and write 2x minus 1 equals u. I'm going to add 1 to both sides, and then divide both sides by 2, and x is equal to 1 plus u all over 2. So now what I can do is I can take x and I can replace it with 1 plus u over 2. So let's rewrite this integral then. Remember, we need the 1/2 out front to balance out the fact that du is actually 2 times dx. So I can't just replace dx with du unless I balance it out with a 1/2 out in front. So that's 1/2 the integral of. Now remember, we're replacing x with 1 plus u all over 2 times, now this square root of 2x minus 1, remember 2x minus 1 is going to be replaced by u with u. We're taking the square root of that, but I'm going to write it with a rational exponent, so that would be times u to the 1/2 and then du. Okay, so let's clean things up a little bit. First of all, this denominator, this is really a constant of 1/2 that I can pull out in front of the integral, multiply it by the 1/2 that's already there. So we're going to have 1/4 the integral of, and then we're going to distribute. Let's take the 1/2 times 1 and 1/2 times u. So that would be u to the 1/2 plus u to the, when we take u to the 1/2 times u to the first, we'll add those exponents, and 1/2 plus 1 is 3/2. So that would be u to the 3/2 and then du. All right, so now we can find the antiderivative by taking it term by term. So let's start with the, oops, I don't need that, hold on. Let's start with the antiderivative of u to the 1/2. So that would be u to the 1/2 plus 1 over 1/2 plus 1. So I guess I'll just go ahead and write this out. That would be u to the 3/2 all over 3/2. We'll clean that up in just a minute. Plus the antiderivative of u to the 3/2 would be u to the 3/2 plus 1 would be 5/2 all over 5/2. Okay, and then this is probably a step you would have done in your head. So this is the same thing as 2/3 u to the 3/2 plus 2/5 u to the 5/2. Remember, dividing by a fraction is the same thing as multiplying by its reciprocal. All right, and so then we can, let's do this first. Let's go ahead and distribute this 1/4. Okay, and then the last thing we'll do is we'll do our substitution or back substitution at the end. So 1/4 times 2/3, the 2's cancel, so that would give me 1/6. So we'd have 1/6 u to the 3/2 plus, now we're going to take that 1/4 times 2/5. Well, there's a common factor of 2 there. 2 goes into 4 twice, so that would be 1/10. 1/10 u to the 5/2. Oh, and I'm forgetting my plus c. Every one of these steps should have had a plus c. And then the last thing we're going to do is back substitute. So let's replace u with what it was equal to. Remember, u was equal to 2x minus 1. So let's replace that then. So we'd have 1/6 2x minus 1 to the 3/2. That's a 3/2 plus 1/10 2x minus 1 to the 5/2, and then plus c. So now let's try an example that has some trig in it. So we have sine squared 3x times cosine 3x. Well, of those two functions, the one that you want to choose for u is the one that's being squared. So let's let u be sine 3x. And now when we go to find the derivative of sine 3x, you'll remember that this is sine, we have a function within a function because we have sine not just of x, but sine of 3x. So that means we're going to have to use the chain rule. So remember, the chain rule for derivative says take the derivative of the outside function. Well, the outside function is sine of something. The derivative of sine of something is cosine of that something. So it'd be cosine 3x. And then times the derivative of the inside function. Well, the derivative of 3x is 3. So I'm just going to turn that around and write it as 3 cosine 3x. And then, of course, that's all, we need to multiply that by by dx. All right, so now when we go to do our u substitution, we can replace sine 3x, we can replace that with u, and then we can take all of this cosine 3x and replace it with du, except that we've got this factor of 3 that we need to balance out. So when we rewrite the integral, we're going to put a 1/3 out front times the integral of u squared, and then cosine 3x dx is all going to be replaced with du. So that simplifies things quite a bit now. Let's find the antiderivative of u squared. So this would be 1/3 times u to the third all over 3 plus c. And then the last thing we need to do is just go back and replace this u with sine 3x. So our final answer will be 1/3, or I guess we can simplify. We can multiply those. Denominators. So we would have 1/9 sine cubed 3x plus c. In example 7, let's let u be 3x minus 1 and see what happens. So we're going to let u equal 3x minus 1. So du will be 3 dx. All right, so this one's going to be pretty straightforward because I can replace u, or 3x minus 1 with u, and then 3 dx can be replaced with du. So our new integral in terms of u would be the integral of u to the fourth du. All right, then we'll find the antiderivative. That would be u to the fifth over 5 plus c. And then all we need to do is go back and replace u with 3x minus 1. So we'd have 3x minus 1 all to the fifth power over 5 plus c. So now let's see how we can use u substitution to find this integral. So as you look at these two factors, e to the x plus 1 and e to the x plus x, as you're trying to decide which one we should use for u, think about their derivatives. And since the derivative of e to the x plus x is going to be e to the x plus 1, that means our choice for u ought to be e to the x plus x. So let's let u be e to the x plus x, then du would be e to the x plus 1 dx. All right, so then as we make our substitutions, e to the x plus x we're going to replace with u, and then e to the x plus 1 dx, all of that can be replaced with du. All right, so we'll rewrite this integral then just as e to the u, not e to the u, the integral of u to the integral of u du, sorry about that. And then the antiderivative is simply u squared over 2 plus c. And then the last thing we need to do is go back and replace this u with e to the x plus x. So instead of u squared, we'll write e to the x plus x parentheses squared all over 2 plus c for our final answer. In example 9, let's let u be x to the third minus 2 and see what happens. So if u is x to the third minus 2, then du will be 3x squared dx. All right, so this will be pretty straightforward. We're going to replace x to the third minus 2. That's going to be u. And then 3x squared dx, all of that can be replaced with du. So our new integral will just look like this, the integral of, and I'm going to go ahead, since that's the square root of u, I'm going to write it with a rational exponent. So that would be u to the 1/2 du, because all of the blue stuff can be replaced with du. And now let's find the antiderivative. That would be 2/3 u to the 3/2 plus c. And then all we need to do is back substitute. So our final answer would be 2/3. Let's replace u with x to the 3rd minus 2. That's all to the 3/2 power. And then don't forget your plus c. In example number 10, a good choice for u is going to be this 1 minus 2x squared. So let's let u be 1 minus 2x squared. Then du will be negative 4x dx. All right, so now this is going to work out great, because 1 minus 2x squared, that's going to be u, and then all of this, negative 4x dx, can be replaced with du. So our new integral in terms of u would look like this, the integral of 1 over u squared du. And then to find the antiderivative, that's going to be easier if we rewrite that at that 1 over u squared as u to the negative 2nd du. So the antiderivative would be u to the negative 2 plus 1, which is negative 1 all over negative 2 plus 1 plus c. Or we might want to rewrite that at let's get rid of that negative exponent. So let's rewrite this as 1 or negative 1 over u to the positive first power plus c, and then we'll do our back substitution. So that would be negative 1 over 1 minus 2x squared plus c. You might remember from a previous example that it's a good idea if we have a couple of trig functions, if one of them is being squared, that's going to be a good choice for u. So let's let u be cosine x. All right, then du, remember the derivative of cosine is negative sine x. So this would be negative sine x dx. All right, so we will replace cosine x with u. So we'll have u squared, and then sine x dx could be replaced with du, except for this negative sign. So to balance things out, let's put a negative out in front of our integral. So this would be negative integral of u squared, and then sine x dx can be replaced with du. So this would be, the antiderivative would be negative u to the 3rd over 3 plus c. And then let's do our back substitution. So that would be negative cosine cubed x all over 3 plus c. So now we're going to switch to definite integrals. We have been doing indefinite integrals. Now we have definite integrals, so we have bounds that we need to worry about. So what we need to remember is when we make our u substitution, right now this integral is in terms of x, and so these would be what we call x bounds. When we make our substitution and rewrite this as a u integral, we'll have to come up with new bounds, because our bounds need to be in terms of u instead of in terms of x. So I'll show you how to do this. Let's start by choosing our u substitution. Let's let this inside function of x squared plus 1 be u. So u would be x squared plus 1. Then du would be 2x dx. All right, so as we go to make our substitutions, we're going to let x squared plus 1 be u, and then we could let x dx be replaced with du, except that we've got this 2, this factor of 2. So to balance things out, let's put the 1/2 out in front of the integral, okay? Now the next thing we're going to do is take care of these bounds. Right now, those are bounds in terms of x, and we need bounds in terms of u. So remember, we're going to use this relationship that u is equal to x squared plus 1. So we've got a lower bound of 0 and an upper bound of 1. Those are in terms of x. So to get our u bounds, we'll just put 0 in for x to get our lower u bound. And then we'll put 1 in for x to get our upper u bound. So let's do that right now. Our lower bound, whoops, let me change the black. Our lower bound, okay, our lower u bound, right now x, our lower bound in terms of x is 0. So let's replace x with 0, and we'll write 0 squared plus 1, which equals 1. So our lower u bound would be 1. And then for the upper bound, okay, our upper u bound, well, the upper x bound is 1. So let's just put 1 in for x, and we'll take 1 squared plus 1. 1 plus 1 is 2. So our upper u bound is 2. All right, then continuing to make our replacements, we're going to replace x squared plus 1. We're going to replace that with u. So that would be u to the third, and then the x dx can be replaced with du. All right, so now we can just evaluate this definite integral in terms of u. So we'll take 1/2, the antiderivative of u to the third is u to the fourth over 4, and then the first fundamental theorem of calculus tells us to evaluate that at 2 and at 1 and then subtract those. So that's going to be equal to 1/2. I'm going to start some parentheses, and I'm going to replace u with 2, so that would be 2 to the fourth over 4, and then minus 1 to the fourth over 4. And now we just have some arithmetic to do. So that would be 1/2 of, let's see, 2 to the fourth is 2 times 2 times 2 times 2, which is 16 over 4 minus 1/4. So that would be 1/2 times 15 over 4. And so our final answer then would be 15 over 8. Now, we don't need to do any back substitution because remember, we changed these x bounds, we changed them to u bounds. So we can just do this whole integral in terms of u and do get the final answer in terms of u. So let's do one more example of a definite integral. So as you look at our problem, it looks like what we'll want to replace u with is, let's let it be this inside function of 1 plus 2x squared. So we're going to let u be 1 plus 2x squared. Then du would be 4x dx. All right, so as we go to rewrite the integral in terms of u, first of all, we're going to replace 1 plus 2x squared. We're going to replace that with u. And then we could replace x with dx. We could replace x dx with du, except for this factor of 4. So to balance things out, we're going to put a 1/4 in front of the integral. And now let's get new bounds. Remember, these are bounds in terms of, I keep saying bounds, but I mean lower and upper limits of integration. Right now they're in terms of x. So let's convert those to terms of u. So our lower bound, or I guess I should say our lower limit of integration in terms of u, would be 1 plus 2 times, I'm going to replace that x with 0. So 1 plus 2 times 0 squared is 1. So our lower bound would be 1. And then to get the upper limit of integration, or upper bound, that would be 1 plus 2 times 2 squared, which is, let's see, 2 squared is 4, times 2 is 8, plus 1 is 9. So that upper bound is 9. Okay? And then, let's see, I'm going to go ahead and write this as 1 over the square root of u, and then that x dx is replaced with du once we put the factor of 1/4 out front. All right, and then let's rewrite that with a rational exponent. So this would be 1/4 the integral from 1 to 9 of u to the negative 1/2 du. All right, and then finding the antiderivative, that would be 1/4 of let's see, that would be u to the 1/2. Negative 1/2 plus 1 is 1/2 divided by 1/2 is the same as multiplying by 2. So this would be 2u to the 1/2. And then we'll evaluate that at 9 and at 1 and then subtract. So we'll have 1/4 times, when I put 9 in for u, u to the 1/2 is the square root of u. So the square root of 9 is 3. So we'd have 2 times 3, and then minus 2 times the square root of 1 is 1. So we have 1/4 of 6 minus 2, which is 1/4 of 1. So our final answer is 1. All right, so I guess that's our last example. So if you have any questions, be sure to ask me when I see you in class. You'll get lots more practice in class, and this is just one of those things, the more you practice it, the easier it gets and the better you get at it. So I will see you in class.